Hi. Well, welcome back to our office here. This will be actually the second of two sort of supplementary lectures dealing with Chapter 9 from the textbook. That's Ordinary Differential Equation Applications. And there's these two lectures. One of them is on quantum bound states, that's today, and how we get an eigenvalue problem with an ordinary differential equation. And the other lecture is on chaotic scattering from a classical system. And both of these have no new algorithms that we introduce, but there's interesting physics, and we use algorithms we've already developed. Today in particular, we'll use a search algorithm along with an ordinary differential equation solver put together to solve the eigenvalue problem. So they're very good examples of how you use the tools you have to do new science and new physics. In this case, they're both very important. So let's talk about quantum bound states and how we solve for a quantum bound state with the computational tools we have. So we've set up a problem here which is meant to be illustrative, as if you were a research scientist living in 1920. Okay? So the question is, does quantum mechanics apply inside of an atomic nucleus? Well, if you look at our picture here, this is a picture of two atoms interacting with each other. Okay? So these E's are electrons, and this is a picture of a nucleus in blue here with a plus sign inside. Now, the picture is not only out of scale, it's completely wrong because electrons don't have any size. They're point particles, so you can't see them. So they'd be minuscule or beyond that. And even if they had some size, say associated with an atom, the circle here, the nucleus itself is more than minuscule. It's like size of the nucleus is like a pinhead in the middle of a football stadium. Okay? So there's a factor of 10 to the fifth, 100,000, multiple hundred thousands difference in size. So the nucleus is really this minuscule point here inside of the atom. And then the question becomes more interesting, which is that quantum mechanics was developed to describe atoms, energy levels of electrons inside of an atom. Can we also use it to describe the energy levels inside of a nucleus? Okay? That was not known. So that's your problem. So what do we know? We know that inside of a nucleus, there's two kinds of particles, most of the time, mainly just two, neutrons and protons. And they both have a mass times the speed of light squared, 940 MeV, million electron volts. Not milli, but million, 10 to the 6th electron volts. Okay? And that's their rest energy. And we also know that inside of this nucleus here, these particles seem to be filling up in energy levels on the order of million electron volts. We know that because if you put that kind of energy in, you get discrete transitions, or you get emissions that indicate discrete transitions of that energy levels. Okay? So we know roughly the size of a nucleus, so this blue dot here is roughly 2 Fermis, or femtometers. In other words, 2 times 10 to the minus 15th of a meter. So that's small. Okay, it's nearly 1,000,000 times smaller than the size of an atom. And so that's all we need to know. Are these facts compatible with the nucleon, the neutron proton, being in a bound state within the nucleus? Okay. So we don't know. We'll have to answer that. So we try to answer that by trying to calculate bound states of neutrons or protons in a nucleus of about that size and see what the energy level comes out. We can ask the similar question, and this was a real serious research question, and it still is a good physics exam question, be aware. Could there be electrons inside of the nucleus? Is it possible that maybe if you bind an electron inside of the nucleus, it could be in these energy levels? So maybe it's not the neutrons and the protons that are in these energy levels, but rather electrons. And that was a serious question. We know that for an electron, its mass times c squared is 1/2 of an MeV. So there's a difference here of just about 2,000 in mass. And that's a hint. The uncertainty principle involves energy or momentum, and there's a difference of 2,000, and trying to put a very light particle inside of a very small space, like a nucleus, would give it incredibly high momentum. And you could try it out. I'll leave that as an exercise for you to figure out at the end when we're done. So how do we go about this problem? Let's look at the next transparency. Okay. So this is the quantum eigenvalue problem, which we'll get to. How do we know that it's an eigenvalue problem? Well, we make a bunch of physical assumptions. First, to keep things simple, we'll assume a stationary state. What a stationary state means is that we'll assume the wave function, which is part of Schrödinger theory, quantum mechanics, which is normally a function of both position and time. We'll assume that the time dependence factors out in just an exponential, e to the minus e times time divided by h bar. And the reason that's important is because then we get what's called stationary states, states whose time dependence just have this simple oscillatory behavior, and we can have eigenstates. It also means that rather than dealing with the time-dependent Schrödinger equation, which is a partial differential equation, which means we have to work a little bit harder, we'll deal with the time-independent, no time, in this Schrödinger equation. So we just have an ordinary differential equation to solve, particularly in one dimension, which is what we'll do. So that's good. Okay, so that's an assumption. Doesn't have to be true in all cases. We'll look for those situations where it is true, and normally bound states correspond to those situations. Bound states. Okay, what do we mean by the term bound state? And this is very interesting because people often will say, maybe not people, students will say, hey, bound state means we have an eigenvalue. No, no, no. That's just the mathematics we use to describe a bound state. What's the physics of a bound state? Well, the physics of a bound state is that we have a state which is confined to one region in space. That's the physics. For whatever the cause is, something is holding that particle in one place, and it's not other places. It stays right there. That's a bound state. It's bound together. And if we now use the mathematics of quantum mechanics, solving a Schrödinger differential equation, and we require that the wave function vanish outside of this region, because a bound state means the wave function is in one small region. Out here, it has to go to 0. If we add that as a requirement to the solution of the Schrödinger equation, we then have a problem called the eigenvalue problem, where we need to solve a differential equation, but there'll only be certain energies, or whatever the eigenvalue happens to be, in this case an energy, that solve the problem. So we're not just solving an ordinary differential equation. We're doing that, but we're also adding on something else. We're adding on this extra condition. So those extra conditions, as we have here, that the wave function vanish when you get far away from the bound region, those are called boundary conditions. True for many differential equations. So we have an ordinary differential equation along with boundary conditions, and that's what gives us the eigenvalue problem. In this case, the values are the energies, so they're called eigenenergies. Eigen from the German word meaning own. So its own particular is a very specific energy. So don't sweat the physics. I've talked a lot physics here. You may be familiar with it, in which case the review is nice. If you're not familiar with it, don't sweat it. All you'll need to know is we're trying to solve a differential equation, and we're trying to apply auxiliary conditions on that differential equation, and that's the eigenvalue problem. So just treat it numerically, and there'll be plenty to do there. Okay? But this is where the physics comes from. Other places in this book, later on chapters, we'll look at similar problems. We'll look at the momentum space bound state problem. We'll solve that as an integral equation, and then we'll end up converting that integral equation into a matrix problem. So that there we'll see the matrix eigenvalue problem. Okay? So that's a good contrast. You may have seen that in your math classes. That's another way of formulating quantum mechanics in momentum space that gives you the matrix problem. Okay? We also, other places in this book, when we talk about the time-dependent, not the independent, time-dependent Schrödinger equation, we'll have wave packets, quantum wave packets, which we can put inside of an attractive potential and try to bind them. That's a much more complicated problem because we have to solve a PDE. We have to solve it in both space and time simultaneously. So we'll put that off. But they're related issues. Here we'll solve the simplest problem, but it still has lots of structure. So let's get on with it. How do we do it? Study this while I take my drink. Okay, so now we just have to formulate mathematically what we've talked about. How do we solve the bound state problem? So as we've said already, we're dealing with a wave function. And the wave function, psi of x, is not an experimental observable, but something closer to that is the modulus of psi of x, because psi could be complex, squared times dx. So this probability, this function, this product, gives us the probability of finding an electron, or whatever mass we're solving for, inside some region of space of length dx. So psi squared is the probability density, and the probability is psi squared times dx. That's what we're solving for. The one-dimensional time-independent Schrodinger equation is given by equation 1. So it's a second order, there's the 2, differential equation, but it has no first-order derivatives, which will come back to, we'll talk about that. It has a potential times psi of x is equal to E psi of x. So this is what we want to solve. In this case, the energy is not known, and only certain values of the energy, known as the bound state energies, will lead to bound states. If we were doing scattering, like in this other special lecture we talked about classically, scattering energy is continuous. Any positive energy, as it turns out, is possible. For the Schrodinger equation, only negative energies can be bound states. Okay, because you can work it out. Positive energies won't give you a wave function that is confined. It gives you a wave function that's a plane wave-like solution, goes over all of space. That can't be a bound state. So how do we solve? Well, we usually don't solve for the energy per se because we make the equation to a simpler form by using the wave vector k or kappa. I use k when I talk about scattering. I use kappa when I talk about bound states. Okay, so the energy, as it turns out, we can assume it's negative here. That'll give us dying exponential solutions, which we'll use for bound states. If we assume the energy was positive, we get plane waves, which can't be bound. So we assume the energy is negative. So the wave vector kappa squared is minus 2m over h bar squared e, minus sign because e is negative. So if we use the absolute value of the energy, kappa squared is always a real number. That's our energy related to the wave vector. So after all that talking, the red equation here, equation 3, is what we have to solve. Second order differential equation, there's a constant here and a simple kappa squared on the right-hand side. So the signs are all right. It looks like equation 1, except the minus signs have been moved around and we've changed the sign here. But this, if we take off here the middle term where there's no potential, that would just have dying and growing exponentials as the two solutions, which is right, because it's the dying exponential that will give us, at least outside the potential, gives us the bound state. So that's what we need. Okay, so let's talk about the next part of this mathematical formulation. How do we do it? So here on this next slide, I put a simple little figure just to give us some understanding. So we're looking to solve for a wave function in a region of space. Here we assume a very simple square wave potential in green. Okay, so that's the binding region where the wave function is going to be bound, and this is the rest of space. So we want to solve, again, equation 3 in red. We just pasted it over here. That's the equation we want to solve. But that, we could just solve that as we want as an ordinary differential equation. Given a value of kappa, you could look for a solution. But we want to do more than that. We want to have confinement built in. So as I said before, confinement is what gives you the boundary conditions. So what are the two solutions? And this is the critical part of this. It's the mathematics or not. If we look at the region where the potential is 0, okay, so if we say, let's leave out the potential term, so then we have d squared psi dx squared is equal to kappa squared, that has two solutions. it has one solution which is e to the minus kappa x, and another solution which is e to the plus kappa x. They are both perfectly acceptable solutions outside of the potential. Okay? And when you deal only with positive, say, when r coordinate, you always say, oh, you can't have growing exponentials. But look, that's not true here. Here what we have is, if we go outside here for, this is the x greater than 0 region, we would say, aha, we can only have e to the minus kappa x here, because that dies off in space, which would keep the wave function confined. If we had e to the plus kappa x, that would grow in space. It might start off small, but then as we get further away, we get larger and larger. That's not a confined bound state. Remember that, because when we solve this numerically, we have to deal with the fact that outside of the potential, both of these are possible solutions, but we only want this one. And for those of you who think, okay, you've heard all this before, whatever is true over here is true in the inverse on that side. So on this side, which is negative x, we can have e to the kappa x is what we want as the solution. Because that's the one that, as we go out here, that's the one that dies off as we move out, away from the potential. So that's the key part. We want the boundary conditions to be the wave function goes like e to the minus kappa x for positive x, goes like e to the plus kappa x for negative x. So that's the boundary condition. That's the extra part that makes this an eigenvalue problem and not just solving an ordinary differential equation. So I said all that. If you can find an energy for which all the boundary conditions are satisfied and the differential equation is satisfied, then we have a solution. These energies don't always exist. Okay? So you can set up some potential. Even here, for example, if I make this square well not so deep, and this is one of the exercises you should do. If I make the square well only this deep, you may not have any solutions. If I make it very, very deep like this, you may have many solutions. Okay? So they can or they cannot exist. Depends on the details of the potential. When we speak of bound states, we speak of often a ground state. And the ground state would be, in this case, the most negative energy solution. So let's draw that again. So this well, particularly if it was deeper, let's say it may have an energy, which on this is an energy scale. This might be the ground state, E0. It may have excited states that look like this. Okay, this would be E1, etc. Or it may not have any. If you make the well deep enough, you're bound to get states sooner or later and keep it attractive. The lowest energy one is the ground state. Now, in quantum mechanics, right here, we have the Schroedinger equation. This term says, what is that term? It's the second derivative. It's the curvature. And it says that the curvier the wave function, the curvier, you like that word? The curvier the wave function, the more energy it has. Haha. Okay? And so if we, and usually there's a minus sign here, okay? So if we want a ground state energy, we want the lowest energy, we want the least curviness, the least curvature to the wave function. If we have a wave function with lots and lots of wiggles like that, that's going to be a much higher energy wave function. The ground state will have as few wiggles as possible, so it's going to be just like that. Okay, so that'll be the ground state. So when we look for the ground state, we're going to look for the most negative energy state. We want that to be nodeless, because if you can find a state with no nodes, it has the least curvature, and we want it to be symmetric, as I've drawn here. So, this other little wave function in here is not symmetric, which means it has a wiggle, means it changes sign. It's a higher energy state. Okay, so we know all those things. So let's go ahead. That's the theory. This next slide talks about the model. So let's take a break. We're almost done. Slide 31 out of 50. Nothing to worry about. Okay. Okay, so here's our model. We could use any potential we want. One of the nice things about the numerical solution is we're not restricted to square wells, which is what most textbooks use because that's the only case where they sort of have an analytic solution. You still have a transcendental equation, but they make believe that that's an analytic solution. Here we could have other potentials. We could have this potential. We could use a much more realistic potential that looks something like this, or a nuclear potential which would look something like come up slowly like that. Then it would be this symmetric on both sides. Okay, or you could do a triangular potential. Anything you want. Feel free. Exactly everything I say here holds, other than it's not a square well potential. It's a more complicated one. So we'll take, for simplicity here, also permit you to compare to the textbooks. But basically, for simplicity and making this argument simpler, we'll just deal with a finite square well. So the potential we have is given by equation 1. It has some depth. Here the depth minus 83 MeV. That's just the number we picked. But notice it's million of electron volts because that's a nucleus. And 83 is just, a reasonably deep well, so we're bound to find eigenstates. Okay? Bound states. And the size, we said, is the absolute value of x, so that's the width of the well, equal to A, 2 Fermis. Okay? So 2 of these 10 to the minus 15th of a meter size. So it's a very, very small by atomic size, and it vanishes absolutely outside of the well. So that's why we picked the square well. It just makes it easy to speak for. So we have 2 differential equations to solve. Within the region of the potential, we have equation 2 here to solve, and that has the second derivative. It has a potential term, a 0 on the right-hand side because we just moved over the kappa squared. And that's inside the well. And outside the well, we have we know we have a solution, equation for which we actually we know the analytic solution. So outside of the well, these are just e to the minus kappa x and e to the plus kappa x are the 2 solutions for that equation. Okay? And even if you didn't have a square well, as long as you had any potential which vanished outside of some range, this equation would still hold. A would be the range of the potential, and then you'd still have these 2 possible solutions. Okay, so that's very good. And in this case here, we have a bunch of constants here, 2m over h bar squared, and for the units we're using to solve this problem, we're telling you these, if you substitute in the speed of light squared above and below, you get these typical dimensions, which if you work out all the constants, this is the value to use here for the constant, 0.05 essentially. Okay? And then we're solving the problem in MeV units. So the energy you get will be MeVs. Okay, very good. So let's go on. How do we solve this? We have a choice. Okay, so here is our potential. We want to solve the Schroedinger equation. And there's 2 things we want to do. One is we want to solve the ordinary differential equation. And 2, we want to impose the boundary conditions. And you have a choice here. I recommend, if you don't know any better, just use your favorite RK4, 4th order Runge-Kutta solution for the ordinary differential equation. It works beautifully. It's robust. It's very effective. In the textbook, and this, go ahead and buy a few more copies if you like it. In this textbook, we also describe the Numerov method. And that's a numerical method similar to RK4, but because the potential we're using, because the Schroedinger equation we're using has no first derivatives, it only has second derivatives, you can actually improve the method to get higher precision, 6th order rather than the 4th, in the same amount of time. Or you can solve the equation more quickly. So if you were doing industrial work, if GM really wanted to solve the Schroedinger equation a lot, you might want to use the Numerov method. But otherwise, RK4 should be fine, unless you have some problems where it isn't. So here's the problem we want to solve. And here is the most critical part. How do we solve it? Some quantum mechanics textbooks, physics textbooks, say, well, what you do is you start with some solution in the middle and you integrate out to infinity. You start here and you move out, and you see if you end up with a dying exponential out here, or a solution which dies off, then you're done, because then you have a confined state. Well, the problem is we're not solving this exactly. We're only approximating the solution. So if we start off with any boundary conditions here inside, any initial conditions, any guess for the wave function, there's always two solutions out here. There's an e to the minus kappa x and an e to the plus kappa x. And if we just integrate outward, a little bit of the error here, even if we start off with what should be a purely dying exponential, a little bit of the error will introduce some growing exponential. So if you go out far enough, the part that's very big here will get smaller and smaller, and the part that's minuscule here, the growing exponential, will get larger and larger. So at some point, the noise will win. Okay, so the rule of thumb, you can't integrate outward on a dying exponential, because then you lose accuracy in every step. You only want to integrate outward on a growing function, because then your accuracy improves. So how do we get about there? Well, we only want to, I'll say it again, we only want to integrate out or in on a growing function. We always want to integrate in. So let's ignore the problem at first and say, aha. So let's start out here on the left with a big function. So on the left, we'll assume the wave function is e to the plus kappa x, and of course x is negative, so that's a dying exponential, and then we integrate in. So on the left here, we assume e to the kappa x, x is negative, good, and we integrate in. So that's good. So this is a function which grows, and we integrate in here, we integrate into that point. Very good. Okay. And this point here is called the matching radius. You can see here, and it's right there where the two solutions match up. Very good. Okay. Then, and of course, once we get inside the well, this can wiggle, but outside it has to be smooth. Then, on the right, we have something else to do. So what we do is rather than just integrating through, calling that the energy, we start out here with e to the minus kappa x, where this is x greater than 0, and we integrate inward. Okay, so that's the trick. So this is a growing exponential as we integrate in. The accuracy gets better. We integrate into this part here, and then we've started out here on a function that did this, and then it can wiggle, and then we see if they agree when we get to this matching radius. So two steps. One, we integrate in on the left, so we're integrating in on a growing function. Then we integrate on the left to the right. Then on the right, we integrate to the left, so we're integrating in on a growing function. Then we match the two. If you don't do the matching, the precision is unreliable. Simple as that. Okay. I've said everything I have to say on this slide. That's it. Okay, so that's the technique. That's the trick. Integrating both ways and matching them together. How do you do the matching? Well, that's what we have to talk about next. How do you do the solution of the differential equation? Either RK4 or Numerov. Leave that up to you. I need a drink, but I probably don't need this kind of drink. Excuse me. I digress. So, how do we match up? How do we do a trial and error search here? Well, here's our problem again. We're trying to integrate in from the left. We have a wave function we've integrated in. Here we have a bit of a wiggle. Well, I'll do it the right way, okay? So what we've really done is we've started out here with a very small wave function. It's gotten bigger, and then when we got inside, it starts to wiggle like this. Fine. And now we integrate from the right, and with a growing function, it grows up, and then it comes up, and it comes up like that. And that's a good case. So here, we want the wave function to match both places. How do we do that? Well, we recall, this is our two exponentials on both sides. We go back to physics. Okay? It's not mathematics. We're saying, well, if it's a physical system like a neutron inside of a nucleus, it has to be continuous. The neutron doesn't jump all around. So the probability will be continuous because physical functions are continuous. And the current is continuous, which means the derivative of the wave function is continuous. Because if you look at the current, it has a derivative of a wave function. If the wave function is continuous, then the derivative must be continuous as well for the current to be continuous. Fine. So what we want is to have psi of x and the derivative of psi of x continuous. But in a way, the value of the wave function doesn't matter because that's just a normalization. And so it's a waste of time trying to require two conditions. So someone clever enough said, aha, let's just require that the logarithmic derivative, that's what it's called, the logarithmic derivative, psi prime over psi, is continuous. Then we don't have to worry about normalization, because if that's continuous, then that means both the function psi of x and its derivative psi prime of x must be continuous. So that's what we'll match on. But be smart. Don't believe anything. We'll solve the problem, we'll get answers, but always go back and look at the wave function, particularly in this region where you have to match to make sure nothing strange has happened. And you'll see why, for example. So, how do you match up? Well, I've seen it, some textbooks, some people in computational classes will say, okay, just guess an energy and keep guessing until they match up. And when you get the guess right, you're there. Well, we know that's true, but it's better for the computer to do all the hard work and not you. Plus, if you were doing this in a research environment or an industrial environment, you want to have some precision. You want to say, I know the energy to 3 or 4 significant places. It's not just what looks good on a graph, which may be 1 or 2, 1.5. So we use some measure of how well it matches. So the measure, I just made this up, is to say, let's look at the logarithmic derivative on the left here. Okay, this is the logarithmic derivative on the left, and we look at the logarithmic derivative on the right. So this is psi prime over psi on the left, and this is psi prime over psi on the right, and we want those two to match up. So we want the difference between the two logarithmic derivatives to vanish. I'll say that again. So what we measure is to say, let's look at the difference between the logarithmic derivative on the left and the right and have that vanish. Ha! This is just like finding the zero of a function. We can use the search algorithm for that. We could. But to keep functions well behaved and make this a reasonable number, I take the plus sign as well on the bottom. That's just to normalize things. So we want this function to go through 0. And if you're worried about the sign, because things can change signs, you could get, these could be very mismatched. You can take absolute values over all these terms. And that's a good idea to do. I left it off here because you see it's a mess, too many things. But then if you're taking absolute values, you know, okay, there's no chance of any weird cancellation occurring other than the one I want for the two logarithmic derivatives to match. Then, of course, you need to go back and check that you have a nice smooth wave function. So that's all you do. And then you can use the bisection algorithm to do that. Okay, to do what? To check that if how big delta is, move along till you get a sign change in delta, then you know, aha, let the algorithm hone in. So you start with some energy. Okay, you start with a guess for the energy, and then you look here. Here we started with, in blue, we started with a blue here curve, is a low energy, which means there's not enough curvature. And you can see we integrate in, this is an excited state, there's not enough curvature here for it to match up. Ah, okay, I can't see that. Match up with the dying exponential here. So if we raise the energy, make it red here, here we raised it a little too much, we got, aha, too much curvature. It's turned over before it could match up well with the dying exponential. So something right in between will just give you the right curvature, and then you'll have the solution. And how many decimal places it is up to you. That's the tolerance you specify. So we give you a code. I can show you the code. I could run it here, but it'll just tell you the answers. Okay? I don't want to do that. Okay? So we have a code here in Python. There's a Java version. The Python one plots up the graphs similar to what we've shown. So here's your exercise. Take the bisection algorithm that you're familiar with, combine it with the ODE solver. If you want, you can use a Newton-Raphson algorithm, which will be faster, but use something which is simpler at first, then you can improve it. That's a good idea. You want a small step size so that you believe the answers are accurate. 0.04 for a weld, which is two Fermis. This is, this is very small. It's like 1,000, 100, 1, 2, yeah. That's exactly about 100 times the size. So, okay, 100th. That's good. Write a subroutine that calculates this matching function, what I call delta, matching for the logarithmic derivatives, and you want that function to go through 0. That's when you have a good solution. And how if you can change the energy only in the 4th decimal place and have it go through 0, then you know, aha, I know what the energy is within 3 decimal places. Okay, so that's how you determine your precision. Okay, do this. Watch it happen. Just don't wait for the final answer. You want to print out for every iteration what the energy is. Limit how many iterations could go, because if you don't have the depth right or something is wrong, you don't want this to go all night. Okay, heat up the rooms too much. Plot up the wave function. See what the wave function looks like, and on the same graph, plot the potential. Obviously, the heights use different measures, but you want to see that the wave function is confined within the potential. How do you know whether it's an excited state or a ground state? You just count the number of nodes. Node list 0 is the ground state. 1 node would be the first excited state, 2 nodes, second excited state. That's the label you use. Okay, so look for a bunch of excited states. If you don't find it, make the well a little deeper until you start finding them. They should be there. Okay, so get the excited state, check for continuity, and then finally, when you're done, verify that we solved the original problem. For these values, are you getting energy levels in millions of electron volts? If you are, aha, so then you're saying, well, quantum mechanics does apply to neutrons and protons within the nucleus. Change the value of the mass, so that's just one constant here, to an electron mass. In other words, make the mass 1/2000th, as big as it was. See what the energies turn out to be. If they're unrealistic, then you're saying, well, I guess you can't bind electrons inside of a nucleus. Nuclei give off electrons, but they're produced by decay of the neutrons and protons, not by actually being bound inside. The energy required would be much too high. But don't believe me, try it yourself. So, a nice example, an important one in the history of physics, an important one for people doing their living, solving atomic problems. This is a nice way to do it. So, go ahead and enjoy yourself. Bye-bye.